Yes, in 1.2, what are we going to do? Okay, first of all, we do determine the size of a matrix and write an augmented or coefficient matrix of a system of equations using matrices and Gauss-Jordan elimination to solve a system of linear equations and solve a homogeneous system of linear equations. We're going to talk about that shortly. Okay, so what's a matrix? A matrix is defined as a rectangular array of numbers, all right? Those can be real numbers, can be complex numbers, quaternions, whatever. There's no limit about what can we input in a matrix, all right? Even functions of x or variables, they can be there in matrices, all right? So each element or number we're going to call it I sub j, all right? Uh, has two indices, the row index and the column index. It goes in order. We first identify the number of rows or the row a particular element is, and then the column, never the reverse, all right? So, uh, the column index, which is j. And a matrix is said to be or to have a size m by n, where m is the number of rows in the matrix and n is the number of columns. All right. Okay, so it's pretty basic definition. And typically we use uppercase letters to denote matrices, and the most typical ones are matrices like A, B, C, sometimes D, typically uppercase for matrices, and lowercase for the elements in the matrices. Okay, so let's have a look at some examples. Let's determine the size of the given matrix A, B, C, and D. Okay, so for letter A, number one, we need to identify the what's it called, the number of rows. How many rows do you see? So the rows are the horizontal ones, the columns are the vertical ones. So 3 rows by 4 columns. What about letter B? 3 by 3. What about letter D? 1 row. 1 row and 8, right? 1 by 8. And what about E? 4 by 1. And in fact, guys, the last couple of examples are, I mean, letter C and D are typically called vectors, a row vector and a column vector. Right now, we're not going to talk about vectors. We're just going to call these matrices, but later, these are really vectors you will see. Okay? Okay, good. Augmented matrices. So augmented matrices, what is this? So we're gonna turn a system of equations like the 2 by 2 case. All we do is write a matrix. Uh, Notice how we have a matrix with a vertical bar right here. Most textbooks do not include that vertical bar, by the way. But I will. I believe also Larson's textbook does, right? This is to denote the equal symbol, and whatever is on the right of that vertical bar, these are going to be the constant terms of the system. Everything else to the left, it's the matrix of coefficients, right? The coefficients of x, the coefficients of y, etc. So here we go. Case by 2 by 2, case 3 by 3. All we do, essentially, get rid of the x, y, z, or x1, x2, x3, etc. Turn it into a matrix. All right. So let's consider the system of equations right here. Okay, so let's write it as an augmented matrix. All right. Okay, so number one, let's write, okay, x, y, z, all of them are there. That is a 2, 3, -1 bar, and then the constant term. All right. Second row. Okay, what do we have? 4x, that's a 4, -1. You see how there's nothing here? What do you think it should be? 0, okay, then 9, all right? I mean, it's kind of redundant or weird to write a 0x, all right? So, and then what about here? Another 0, isn't it? 0, 3, 4, and another 0, okay? This is what we typically call encode a system into a matrix. And then we're going to do the reverse. That's actually example number 3. Decode a matrix into its corresponding equations, okay? All right. In this case, what do we have? 1, 0, 0, negative 3. Okay, what does the 1 really mean? That 1 means the coefficient of x, right? Okay, so x, but do we really need to write 0y and 0z? Don't do it. X equals to negative 3. What about here? What about the second row? 0x plus 1y plus 0z equals to 2. Y equals to 2. And then the third row, 0x, we don't need to write it, plus 0y, we don't need to write it, plus 1z, we need to write it, z equals to 5. Right? That's what we get. So going back and forth, encoding into a matrix, decoding into a system. Okay, so okay, what's next? Okay, Gauss-Jordan elimination to solve a system. Okay, so again, we're going to do exactly the same process we just did at the end of the previous section. However, we're going to do that with these matrices, no longer x's, y's, and z's, or x1, x2, etc. No, it's a more compact notation. It's better than having to write a lot. It takes a lot of time to write all of those, all right? So, and well, um, Gauss-Jordan elimination, what can we do? Well, rather than talking about equations, now we talk about a row. We can interchange rows. We can multiply a row by a non-zero scalar or constant, or we can add a multiple of a row to another row. Aren't those the exact same rule or row equation operations from the previous section, except that now we have matrices and we do this with the rows. That's all. All right. Okay. So let's consider the augmented matrix here. All right. Let's consider that. Performed, okay, just for practice. I mean, it is more like a prep, like a preparation before we actually get into solving a system. Hopefully, we get the chance to do that, all right? Yeah. Okay, so, okay, they're asking us to perform this operation, which is negative 3 row 1, okay, to obtain a new row 1. Okay, that means the other two rows remain the same. Okay, 6, negative 1, negative 4, 10, 7, 1, negative 1, 5. Okay, so let's do the operation for the first row. I'm going to multiply by everything by negative 3. So negative 3 times 2 is that negative 6. Negative 3 times 4 is that negative 12. Negative 3 times a negative 1 is that a 3. And negative times a negative 3 is that positive 9. All right? So we obtain a new row 1, having the remaining two rows intact, in fact. All right? Okay, guys, so for the same matrix, letter B, they're asking us R1, double arrow, R3. What does that mean? This means to interchange row 1 with row 3. Okay, so row 1 with row 3. That means, okay, again, the second row remains the same. 6, negative 1, negative 4, 10. Okay, and let me bring this third row to the top. 7, 1, negative 1, 5, and 2, 4, negative 1, and the negative 3. Okay? And that accomplishes the operation. Right? Just interchanging a row. We didn't even calculate, multiply, add, whatever, anything. All right, guys. The next one, let me see. Multiply the second row added to the third row to obtain a new third row. Okay, so let me write that down. Okay, 2 times row 2 plus row 3 to obtain a new row 3. All right. Guys, in this case, I'd like to do this operation on the side. Let me show you how I do it. More than likely, when you learn this, if you did it in college algebra or pre-calculus, more than likely you were just asked to do it in your head. Okay, let me show you how I do it by hand. Okay, so let's see. Let me do the operation here on the side. Okay, so the row 2, which is 6, negative 1, negative 4, 10. Okay. 6, -1, -4, 10. What else are we going to do here? Okay, the first one remains this. No, 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 no. Yeah, I see, I see. And I'm going to multiply this by what? By 2, right? And then I'm going to add it to the third row. 7, 1, -1, 5. This is what we're going to do. What is that? 2 times 6 plus 7, 19. 2 times -1 plus 1, 2 times -4 minus 1, 2 times 10 plus 5. That's the new third row. That means the first two rows remain exactly the same. 2, 4, -1, -3, and then 6, -1, -4, 10. And then if we replace 19, -1, -9, and 25. All right? Especially this third operation, that's the one that we will use the most. All right? So you guys already know what matrices are and how they relate to, at this point, how they relate to systems of equations. That's number one. Number two, what's an augmented matrix, which really relates to that system of equations. And then what are the operations that we do? Essentially, exactly the same ones as in equations, but with rows, right? With matrices. Okay, more definitions. Row echelon form versus reduced row echelon form. Okay, so let's have a look at this definition. So a matrix is not necessarily an augmented matrix. It could be any matrix. So it's said to be in reduced row echelon form if it satisfies all four conditions below. However, on the other hand, it's just row echelon form, which is not the same as reduced row echelon form, if it only satisfies the first three conditions, and not the fourth. We'll see about it. Okay, so what are those conditions? Number one, if there are any rows of all the zeros, then they are at the bottom of the matrix. If a row does not consist of all zeros, then its first non-zero element or entry, that is the leftmost non-zero from left to right, right, the leftmost zero non-zero entry must be a one. And that's what we call a leading one, or sometimes we call this a pivot, right? That's our pivot or our leading one. Number three, in any two successive rows, neither of which consist of all zeros, careful with that, the leading one of the lower row has to be to the right of that leading one, to the right of the on the what is it? To the right of the leading one on the in the higher row. All right, because we want to make this look like a staircase. That's what echelon means. It means like the step of a staircase, right? That's echelon. So we want to make this staircase shape on a matrix, right? And number four, if a column consists of a leading one, then all the other entries must be zeros above and below, depending on where we are in the matrix. Okay, so let's have a look at this. All right. So this matrix, letter A, do you think it's in reduced row echelon form? Do you see this, the staircase shape? All right, so that's a yes. All right. Let me skip letter B. That'll be a weird case, okay? Let me do letter C. What do you think about letter C? Is that in reduced row echelon form? So, okay, so in this case, this could be a bit confusing. So number one, we have a leading one here with zeros below, right? We have a leading one here with zeros above and below, okay? And we have a row of all zeros, okay? So this is a yes, all right? So this is a yes. Letter D, okay, what do you think about letter D? Why not? The two, we we wish this were a one actually, a leading one, right? And well, we still have the zeros above and below, but that's not a one in the, it's a two. So, okay, what about the zero matrix, the matrix of all zeros? Is it in RREF or not? That's an interesting one. Yes, the rows of all zeros, good. Yes, what's up? What's up? Okay, here's the tricky part. Okay, actually, what's gonna make it a reduced row echelon form. That is okay. We have leading ones, right? So if we have leading ones to the leftmost, well, then it's in reduced row echelon form. But you don't see the leading ones, right? Okay, here's the analogy for this to call it a yes. Let's say, um, let's say I'm gonna give, let's say let's say I will bring free treats to all cats that are dressed with a pajama. All right. Are there any right now in the classroom? Right? No, there aren't any. So I didn't give away any treats to the cats because there were no cats. So, but that doesn't mean I broke my promise, did I? Same over here. The leading ones are not there, but we still have the row zeros. All right. See what I'm saying? So that's why it's a yes. All right. So let's solve a system of equations using row operations. It's gonna be perfect timing. Okay, hopefully. Okay, so let's write an augmented matrix that is oh wait, that's blue. 1, -2, 3, bar 9, -1, 3, what is that? 0, -4, 2, -5, 5, 17. Okay, how are we going to start the problem with matrices, no x's, y's, and z's, etc.? Okay, so we want to start with a leading one in the element 1, 1. We're going to keep reducing the matrix, and we want a 1 in the 2, 2, and then a 1 in the 3, 3, etc. And if we have 17 equations with 17 unknowns, we keep the same pattern. All right. Okay, do we have a 1, 1 here in the 1, 1 element? Perfect. Okay, so we need to zero the -1 and the 2. Okay, how do we do that? Well, number one, let's indicate the operations. Do you guys agree that adding the first row with the second row actually turns this into a 0? So that is row 1 plus row 2 equals a new row 2. How would you make a 0 where the 2 is? So, in other words, 1 times what number added to 2 equals to 0? -2. So, -2 row 1 plus row 3, that goes to row 3, right? Okay, so that means the first row remains the same, okay? 1, -2, 3, 9, okay? And okay, 1 minus 1, is that equal to 0? 3 minus 2, is that equal to 1? And 3 plus 0, is that equal to 3? And 9 minus 4, is that equal to 5? Okay, so that's the first operation. Score on the first operation. Let's have a look. Operation. Okay, I'm going to multiply the second row by, what is that? -2, okay? And then whatever I get, I'm going to add it to the third row. That's going to be our new row 3. Okay, so -2 times 1 plus 2, is that equal to 0? Negative times a negative equals positive. 2 times 2, which equals to 4, minus 5 equals -1. All right? -2 times 3, is that equal to -6 plus 5? Is that -1? Another -1? And -2 times 9, is that -18 plus 17? Is that another -1? Okay. So what do we have so far? We have a 1 and zeros below. Okay. So we're good with this Gauss-Jordan elimination. We're following the definition that whenever we have a leading one, all all the entries below or above must be 0. Now let's kill it for the second column. Okay, so the question here is, what row operations here? Okay, so now we're going to move to the next pivot here, all right? The next pivot, which will be the 2 2 element, which by the way, it's already a 1. However, if for whatever reason you had like a 3 or a 7, then number one, find a way to interchange rows so you don't deal with fractions. And if there's no way around, well, fractions will do fine. However, in this case, we can turn this into a 0 and we can turn this into a 0 because we have nice integers. All right. So actually, how about row 2 plus row 3 to obtain a new row 3? Do you guys agree with this operation? And lastly, oh, check this out. We wish we had a negative 2 here, all right? We can make our wish come true, all right? How do we do that? Multiply that by 2, all right? Multiply by 2, so 2 times row 2 plus row 1 to obtain a new row 1, okay? That means this time the second row, the row containing the current pivot, it's the one that's going to remain the same. It remains untouched. 0, 1, 3, and 5. Uh-huh. And okay, let's do the operations. Okay, so 0 plus 0 is 0, 1 minus 1. So that's 0, 0, and then 3 minus 1. What is that? 2. And 5 minus 1, is that equal to 4? And okay, let me use a different color for this. Let me do the second row multiply by 2, and whatever we get, add it with the first row, right? The nice thing about this is that when even if you multiply this row by a non-zero number, you don't mess up the zeros and you don't mess up all the pivots. They remain there. All right. If for whatever reason you get those messed up, you are doing the wrong operation. So double check. All right. Here we go then. So 2 times 0 is 0 plus 1 equals to 1. 2 times 1 equals to 2 minus 2. Is that equal to 0? 2 times 3 equals to 6 plus 3. Is that equal to 9? And then 2 times 5 equals to 10 plus 9, 19. Okay? Do you see how we have 0 above and below? We're going with the staircase. We're going with echelon form, reduced echelon form. All right? Okay. Now, okay, so we're done with 1, 1. We're done with 2, 2. Let's go to 3, 3. Do we have a 1 here? Okay, we wish we had 1. Okay. We can make our wish come true. What do you think we should do to this row? Like have row 3. Mhm. 2 minus. So 1/2 row 3 to produce a new row 3 for us. So we do one operation at a time, right? First turn it into a leading one and then do the necessary operations. Okay, so that means the other two rows remain the same, 1, 0, 9, 1, 0, 9, 19, 0, 1, 3, 5. And well, just divide everything by 2. So that's 0, 0, 1, and 2. Right? What do you think we should do here? Well, we want to turn this 3 into a 0 and turn this 9 into a 0. Okay? How do we do that? Uh-huh. Row 3 by negative 3 and add it to the second, and the other operation by negative 9, right? Okay, so that means negative 3, row 3, plus row 2 to produce a new row 2. And negative 9, row 3 as well, yes, plus this time row 1, right? And that to produce a new row 1. Okay? Okay, let's execute the operations. Right, okay, let me do different colors. Okay, let me first multiply by -3. Okay, -3 times 0 equals to 0 plus 0. Oh, first of all, let me write down the matrix. Okay, whoops, too big. The third row remains the same in this case. And okay, here we go. -3 times 0 is 0 plus 0 equals to 0. -3 times 0 equals 0 plus 1 equals to 1. -3 times 2 equals to -6 plus 5. Is that equal to -1? Oh, I forgot the 0. Okay, -3 times 1, that's a -3 plus 3 equals to 0 here. Okay, so we're done with the second row. Now let's get the new row 1. Okay, so what did we say about it to multiply by -9, right? Okay, -9. All right. So -9 times 0 equals to 0 plus 1. Is that equal to 1? -9 times 0 plus 0. Is that equal to 0? Do you see how these zeros do not get messed up? The more we go, the further we move through the echelon form. Okay. And then -9 times 1. That's a -9 plus 9. 0. -9 times 2 is that -18 plus 19. 1. And guys, a matrix in reduced row echelon form. Okay, we may now go ahead and decode this matrix into a system, into the actual, well, yes, technically a system of equations. However, this is going to leave us with x equals to 1, y equals to -1, and z equals to, what is that, 2? Let's just properly write it down. That is x, y, z as an order triple. 1, -1, 2. Final answer. Okay. All right, let me see what's next. Okay, there's another example here. Uh, However, I think this is a good moment to stop. Right? I don't think I'm gonna have enough time in 7 minutes